Hey guys, James here, how are you doing? So Veritasium recently uploaded a video showing a little experiment, and he asked people to first predict the results, and then after they'd seen the results he asked people to make video responses trying to explain why the results were as they are. So here's just briefly what the experiment was.
Alright, here is the setup. I have a rifle mounted vertically, and we're going to shoot a bullet into this block, right into the middle of it. And so obviously the block is going to go flying into the air. But we're going to do this again, and instead of firing the bullet right into the middle of the block, we're going to shoot it off to one side. And I want you to make a prediction. Will that spinning block, when we hit it to one side, will it go the same height as this first block? Will it go not as high, or will it go higher?
Okay, so that's the basic setup. I don't want to spoil this for anybody, so I'll leave a link to the original video down below, and I urge people to watch that before carrying on with this video. I'm going to give people a few seconds to do that, and then I'm going to show what the results were.
Now check out the high-speed footage. You can clearly see that both blocks go to the exact same height, even though one is rotating. And that's a bit strange because they were both hit by the same type of bullet from the same rifle, so presumably it had the same kinetic energy.
Personally, I did manage to predict the right answer, not because I'm some sort of genius, though of course I am, but simply that them both going to the same height is the unexpected answer, which would make for a more interesting video. The obvious answer is of course that the spinning block wouldn't go as high because more energy is being transferred into making the block spin, which otherwise would have gone into pushing the block up vertically. Now, as for why they ended up both going to the same height, I don't have a complete answer, but I do have an answer, and I also have a refutation to the most common answer, which was put in the comment section of the video. The most common answer I saw in the comment section was that the amount of energy required to spin the block is absolutely negligible compared to the amount of energy required to push the block up vertically. Now, I didn't buy that explanation for 1 second. I know that spinning things does in fact take quite a lot of energy, and there's enough data in the video to actually test that hypothesis with maths. So before we do the calculations for that, we're going to need to know a few things. So firstly, I'm going to guess that the height was round about 1 metre. The weight of the block is about 600 grams. Now, this is not an important, the weight is not an important figure. We need to know the ratio of spinning energy to vertical kinetic energy. And if they weighed 1,000,000 times more, we'd simply times both numbers by 1,000,000, so it would counter out anyway. The diameter I'm guessing to be around about 15 centimetres by how the block was held, and the spin is about 666 RPM. Now, how we got to this figure is that it takes 0.45 seconds to freefall 1 metre from a standing start. So 0.45 seconds up, 0.45 seconds down gives us 0.9 seconds. Looking at the slow motion footage, I counted 10 spins, so we take those 10 spins, divide it by 0.9 and times it by 60 to give us our RPM. Okay, so I took those numbers and I used them in some online calculators. The first thing I wanted to know was the potential energy, which turned out to be 5.88 joules for 1 metre and 0.6 kilograms. Now, in theory, this should be the same as the amount of vertical pushing energy which is put into it to start off with. So 5.88 joules for that. And next we're going to look at the spinning energy. For this I used a flywheel energy calculator and used the figure for a disk. Now people are going to point out that this isn't perfect because the block is not a disk, it's a cuboid in shape, but this is accurate enough for what we're doing. It's enough to show that the amount of energy is not negligible. So this gave us 4.105 joules. So in total at 1 metre that means that 40.9% of the total kinetic energy is put into the spin. Okay, so hopefully everybody agrees there that 40% is not a negligible amount. Now supposing I got the estimate wrong, supposing it went to 2 metres instead, would that change things very much? Well, let's have a look at the maths for that as well. So, of course, it's also it's going to spend more time in the air at 2 metres, so 0.64 seconds down as opposed to 0.45, giving a total of 1.32 seconds up and down compared with 0.9. And a total energy of 11.76 joules being transferred to pushing it vertically. So that's double what it was at 1 metre. Now let's have a look at the spinning kinetic energy. So first, of course, we have to adjust the RPM because that's 10 spins over 1.32 seconds as opposed to 0.9 seconds. That gives us 1.911 joules of spinning kinetic energy, which brings us to a total of 13.9% of the energy going to spinning it. Again, this is not a negligible amount of energy. It would certainly be very, very noticeable in the footage. Another common argument I saw in the comments section was that supposing this is the block here, there is, although there's more kinetic energy in the side which is spinning up, there's less kinetic energy than the side in the side which is spinning down compared to the centre, and that this directly counteracts, and so there's no additional energy in the system anyway, so it doesn't matter. Now this fails for 2 reasons. Firstly, kinetic energy is proportional to the square of the velocity, so if that going off that argument, although there's less energy on the side spinning down, this is more than counteracted by the energy of the side spinning up. Also, if we're to take that argument to its logical conclusion, it must work for any velocity including 0, and if that was the case, then it would take 0 energy to make something spin at 600 RPM, which is clearly absurd. So I can see 2 possible answers. The first one, and the least likely, is that there's simply an irregularity in the power of the gun, and so because we've got that irregularity in the power of the gun, the second one was just happened to be that much more powerful. Now, this would certainly be a very good argument in terms of making sure that you have an adequate sample size in your experiments, but I don't think it's an interesting enough answer for the video. So instead what I'm going to say is that the kinetic energy exchange between the bullet and the block isn't going to be 100% efficient. There's going to be energy loss to sound and heat and that kind of thing, and that in the non-spinning one there is more of this energy lost than in the spinning one. So for example, for sound, here's the block here, with it going in the centre, quite a big impact there, whereas if it's on the side, a lot less sound, and it just so happens that the amount of sound, the amount of energy which becomes sound and heat is exactly the same amount of energy which goes into making the block spin. Now, is it the case that the energy directly counteracts only when you have that particular size block with that particular wood, using that particular gun with that particular type of pellet, and using the side angle at exactly the right amount? Or is it the case that this is simply always the case regardless of what type of block you use and what type of gun you use? I'm really not sure about that at the moment. I'm guessing that it's always going to be the case and there's going to be some clever answer for why that is, but I don't know. So if anybody has a better answer for why this is, then please leave me a video response. Thanks for watching, comment, rate, subscribe, and I'll see you soon. Bye.